We have a spring with a spring constant of 68 newtons per meter. So K is 68 newtons per meter. And it hangs from a ceiling when a 12 Newton downward force is applied to the free end of the spring. So we have a 12 Newton force that's pulling the spring down. So that's going to be the force on the spring. That's 12 Newtons. And the question is, how much is it going to stretch? We know that that is X, the change in spring length. So this one's really straightforward. It's Fs is equal to Kx. So we have 12 newtons is equal to 68 newtons per meter times X. And X, when you do the math, comes out to 0.18 meters. So that's choice 1. This one is tricky. Okay, so we have a diagram below with an object of mass m, and it's located on the surface of the moon. So that's at radius r. It's attracted to the moon with gravitational force F. So we have F, and an object of mass 2m, so we have this double mass, so the mass is changed by double, at an altitude equal to the moon's radius r. So this r here. And this is where the trick is. We have to do it from the center. So that distance, r, is not right. It's really 2r. So the question is, what happens to the force? Well, we know that we have g m1 m2 over r squared. And what have we changed? Well, we've doubled mass 2. So I'm going to put in a 2m2. And we have doubled the radius. So that's 2r, but remember, that's squared. So that's 2 on the top, and 2 squared is 4. That's 4 on the bottom, so that's a half. So a half is F over 2. Okay, the magnitude of the gravitational field near the Earth's surface is represented by which of these formulas? Now, if the question had said, what's the magnitude of the force? Then we would say it's this answer right here. But the question said, what's the strength of the gravitational field? Well, we know that Fg is equal to this, but it's also equal to mg. So if we're looking for g, let's just divide through by the mass. We say g is equal to Fg over m. What's g equal to? Fg over m. Okay, get your calculators out for this one. We have 2 soccer balls, 0.425 kilograms each. And they are separated by a distance of 0.5 meters. And the question is, what is the magnitude of the gravitational force of attraction? So that's going to be our formula, Fg equals g m1 m2 over r squared. So we have Fg is equal to, and remember, we have to look up g on our reference table. And that's going to be 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared times 0.425 kilograms times 0.425 kilograms. And we're going to divide all of that by 0.5 meters squared. Okay, so I'm going to walk through this. So we have 6.67 using our exponent key, negative 11th, times 0.425 times 0.425, and I'm going to hit equals. That's going to give me the number on the top. Now I'm going to divide by 0.5 and square that, and that gives me a value of 4.82 times 10 to the minus 11th newtons. And there is our answer right there. All right, we have a spring with an unstretched length of 0.4 meters. So it's 0.4 meters when it's at equilibrium. And then the spring is stretched to 0.6 meters when a 10 Newton weight is hung from it. So they put this 10 Newton weight on there, and the question is, what's the spring constant? So we can do Fs is equal to Kx, and the force on the spring is 10 Newtons. We're looking for K, the spring constant. And what's X? Is it 0.4? Is it 0.6? Remember, X is the change in length from equilibrium. So that's going to be from there to there. So that's final minus initial. So that's actually going to be 0.2 meters. And the answer for that is 50 newtons per meter. All right, so we have a planet X with a mass of 10 kilograms weighing 40 newtons. What's the magnitude of acceleration on the planet? So we're looking for g. So this one is very straightforward. We can just do Fg equals mg. We know that it has a 40 Newton weight. It has a mass of 10 kilograms. And we're looking for g. Dividing through, g is equal to 4 meters per second squared. In this problem, this is basically the same problem we already did. The difference is they did the diagram for us. So we know that x is this change in length of 0.25 minus 0.15. So this distance x is 0.1 meters, 10 centimeters. So it says, what's the spring constant? Well, we can just do Fs is equal to Kx. The force added to the spring was 35 newtons. K is what we're looking for, the spring constant. And X is the change in length, so that's 0.1 meters. And when we divide 35 by 0.1, we get a spring constant of 350 newtons per meter. Number 8, this is a trick. A 65 kilogram astronaut weighs 638 newtons on the Earth. What's the mass of the astronaut on the surface of the moon where gravity is 1.6? So they would weigh less, but they're not asking for the weight on the moon. They're asking for the mass. And we know that mass does not depend on location, so the answer is 65. Number 9. So we have a graph, and it's weight versus mass. And on the surface of planet X, determine the acceleration due to gravity. So change in y over change in x, change in y over change in x is our weight, Fg, over our x, which is mass. And we know from Fuga Mugga that if we divide through by m, we're left with g. So that's g. In other words, the slope of the line is the strength of the gravitational field. So if we go from 0, 0 to 18 and 6, we can say that the weight changed from 0 to 18 by 18 newtons. And we're going to divide by 6 kilograms, the change from 0 to 6. And that's going to give us a gravitational field of 3 meters per second squared. Okay, very similar. We've seen 2 of these already. We have a vertical spring with a spring constant of 100 newtons per meter. When an object is attached to the bottom of the spring changes its unstretched length from 0.5 to 0.65. So what is x? It is the change, so that's 0.15 meters. And the question is, what was the weight attached to it? So we're looking for the weight that stretched the spring. What's Fs? So that's just going to be Fs is equal to Kx. And we have Fs equals 100 newtons per meter times 0.15 meters. And that's going to give us the force of the spring, which is equal to the weight that's being pushed down, of 15 newtons.